In this video, we'll be looking at how to add and subtract functions. So on the graph to the right, there is one function that shows college enrollment between 1995 and 2010. And there is another function that shows the university enrollment. If you look at the very top function, it is the total enrollment. So this top function is the sum of the college and the university functions. The way we find this sum function is by adding the y-coordinates of the corresponding points. So for example, for the year 2002, I have a point here on the college function. It is about 250,000 students. I have the university around 350,000 students. If we add those up, that's 600,000 students, and that's exactly where the point for 2002 for the total function would be. So in terms of notation, if you're given two functions, f of x and g of x, the sum can be shown as f plus g of x or f of x plus g of x. And this function can be found by adding the functions algebraically or graphically. And again, it's about adding the y-coordinates. And in terms of the domain of the sum function, it consists of all the values that belong to the domain of both functions. So if you compare the domain of the two functions, you find that overlapping region, that would be the domain of your combined function. So let's look at our first example. F of x is equal to x, so just a linear, and g of x is equal to 1 over x, so our base rational function. We want to find f plus g of x. So let's start it off algebraically. So the combined function will be x plus 1 over x. Now, when you see something like this, it is pretty common to get a common denominator to unite the fractions. So I will do that. If I want both fractions to be over x, I'll multiply that first function, top and bottom, by x. And then we'll have x squared plus 1 in the numerator all over x. And from here, of course, we would like to add a restriction. And I can graph this function using this equation because we have rational function knowledge. So let's see what we know here. We know that there's going to be a vertical asymptote when x equals 0 because of our restriction. In terms of an x-intercept, I would set my numerator equal to 0 and solve for x. But when we do that, we try to square root -1, which can't be done. So there are no x-intercepts. And then we have to see if we have a horizontal or oblique asymptote. Because the degree in the numerator is 1 higher than the denominator, this does have an oblique asymptote. So I'm going to go ahead and do some long division here. Now I'm going to write x squared plus 0x because that middle term is missing. And now let's see. What times x gives me x squared? That would be x. Okay, that's 0. Then I bring the 0x down. What times x gives me 0? Well, that's just 0. So we're kind of done here. Our oblique asymptote is y equals x. And now we can use that information to start roughly graphing. So I'm going to put my vertical asymptote here at x equals 0. My oblique asymptote has a y-intercept of 0 and the slope is 1, so rise 1, run 1, which means this is my oblique asymptote. Oh, I didn't get a y-intercept, so if I set x equal to 0, well, there's an asymptote there, so there is no y-intercept and no x-intercept. So from here, I can try a test value. So I'm going to find f at 1 and f at -1. So let's see, if we plug in 1, we would have 2 over 1, which is 2. So I'll plot that point. And if we plug in -1, we would have 2 over -1, which is -2. There we are. And I think from here, just following my asymptotes. Although I could double check my end behaviors by plugging in 100 and -100 for long term, and plugging in, let's say 0.01 and -0.01 to see the behavior around the vertical asymptote. But there we are. There's our graph. Now, when we found the graph for this combined function, the combined function was something familiar to us, so we were able to use our prior knowledge to graph it. But if it were something that's not very familiar, we can always create a table of values for the original two functions and then add those y values. So I'll show it that way as well. Okay, so let's put a little table of values here. And I'm gonna do it for x first. And I'll just go from, let's say, -3. And because y equals x, well, the y coordinates are the exact same as the x coordinates. For my next one, I'll put y equals 1 over x using the same x values, because when I'm adding my y coordinates, it has to be for corresponding y coordinates, so when the x's are the same. So we'll have -1/3, -1/2, -1, not applicable, no solution there because of the asymptote, then 1, 1/2, and 1/3. Now our combined function is going to be the sum of those y's. So I'll keep my x's the same. And then let's see, I'm going to add -3 and -1/3. That would be, if we get a common denominator, so -9/3 plus -1/3, -10/3, or -3.3 repeated, which I think I went a little bit too low, but it's close enough. And then -2 plus -1/2, it's -5/2, so -2.5, perfect, that's what I had. -1 plus -1 is -2. At 0, I have 0 plus not applicable, so this also will not exist, because if one point doesn't exist, the sum can't exist. Then for 1 plus 1 is 2. 2 plus 1/2 is 5/2. 3 plus 1/3, 10/3. And that would be our combined function, and we could graph from there. And if you look at what we actually graphed based on our prior knowledge, it's the same points. And then in terms of the domain, I'm going to start off by just showing the domain of f at x. So the domain of f at x is just -∞ to infinity, because it's a line. The domain of g of x, because we know it's a rational, x can't be 0, the domain is -∞ to 0 and 0 to infinity. Or we can write it in the other notation and just say x can't equal 0. Our combined function will be the domain that fits both of these domains. So it's going to have to be the same thing as g of x, because g of x had some sort of restriction. And that's exactly what we see graphically with that visual. Now, let's try the difference of functions, and it's going to be the exact same scenario. Our notation is now f minus g of x, which is f at x minus g of x, and the same idea with the domain. The domain of the difference function will be the domain of both functions, that overlapping region. So once again, we will do an algebraic way and a graphical way. So f minus g of x will be x subtract 1 over x, and once again, getting that common denominator, x over 1 will get multiplied by x on the top and bottom, so we'll have x squared subtract 1. And again, same restriction, x can't be 0, which means we have a vertical asymptote in the same place again. I'll go ahead and graph that while we're here. We have, this time, we have x-intercepts, because that numerator, you can either just set it equal to 0 right away, or I could have gone a little bit more here and factored the numerator, because it's a difference of squares. And now I can see I'm going to have an x-intercept at -0 and 1, 0. So I'll go ahead and plot those. And now, again, there is no y-intercept for this one because of that asymptote. But this one, once again, will have an oblique asymptote because the degree on top is 1 higher. So again, I'll do my division here. X times x will give me x squared. When I bring the 0x down, I'd technically be adding 0 to get that 0x. Because then when I bring the -1 down, I can't go further. So the oblique asymptote is once again y equals x. And now, based on how my points are related to the asymptotes, thinking we're going to have something like this. Okay, and in terms of test values, I've already tested 1 and -1 because of the x-intercepts. I could always test 2 to get a little bit more, so why not do that? So let's see. We would have 2 squared minus 1, so that's 3 over 2, so 1.5. I'll plot that. And f at -2 will be -2 squared minus 1, which is also 3, but over -2, so -1.5. Okay, and now I'm pretty confident in this shape. And there it is. And I could do the same thing with the table of values as I did before, where I just subtract the y values. I'm not going to do the table of values for the original functions again because we had them from above. So I'll just remind us of what those values were and we'll subtract them. And we have to make sure we subtract the x minus the 1 over x y coordinates. So we'll have -3 subtract -1/3. So that would be -8 over 3. Okay, so -2.67, something like that, which looks about right. For -2, we'd have -2 minus -1/2, which is -3 over 2, which is what we had found before. For -1, we'd have -1 subtract -1, which is 0. At 0, we had that asymptote, so no thank you. At 1, we have 1 minus 1, which is 0. 2 minus 1/2, which is 3 over 2, which is what we had. And then 3 minus 1/3, which is 8 over 3. So those would have been points from our table values if we didn't know how to graph that combined function. For example, you are combining two functions that when you combine them, it's not a familiar function like this rational one. And our domain is the same as before because of the asymptote. So you can write it like that, or of course we can write x as an element of all real numbers such that x cannot equal 0, whichever you prefer. All right, one more little example here. The stopping distance for a car is the distance the car takes to stop from the instant there is a need to stop until the car has actually stopped. Stopping distance changes depending on the speed the car is traveling at. This is shown on the graph to the side. So stopping speed right here. The faster you're traveling, the bigger your speed, the bigger the stopping distance required. For example, if you're traveling at 100 kilometers per hour, you need 90 meters to stop. The distance traveled during the time it takes a driver to respond to a need to brake situation is called the reaction time. The reaction time distance also depends on the speed of the car. So again, using 100 kilometers per hour, if you're traveling at that speed, you have a reaction time distance of 20 meters. So in 20 meters, you'll realize, oh my God, I need to brake. But at that speed, it takes you 90 meters to actually stop the car. So that means stopping distance is made up of your reaction time plus the actual braking distance that is required. So we need to sketch a graph to represent this braking distance. So I'm going to turn this into functions. My stopping distance, let's say S at X, the reaction time distance R at X, and the braking distance B at X. So if I want braking distance, I'll bring reaction time over, and the braking distance will be the stopping distance minus the reaction time. So I'm going to take my Y values and subtract them. So I'm going to start with 100 because I've been talking about it. So at 100 kilometers per hour, stopping is 90, reaction is 20. 90 minus 20 is 70. So I'm going to plot that point. Then let's look at 80. At 80, we're at 59 and maybe 16. And 59 minus 16 is 43. So I'll roughly plot that. At 60, we're at maybe 35 for the stopping distance and at maybe 12 for the reaction time. If we subtract those, 23 roughly. Then we have 20 minus maybe 8, so 12. Then we have 10 minus 4 maybe, so 6, and 0 with 0. And then we can roughly graph that. This portion does look a little linear. And there we are. There's our braking distance. So we just subtracted our Y values because in this scenario, the two functions that we were given, we weren't given their equations to actually be able to subtract them to try to graph using our prior skills. So here we did really have to use those Y coordinates. And that's it for adding and subtracting functions.